Thank you. So let me begin by thanking the organizers for inviting me to this wonderful conference to honor David, and happy birthday, David. Don't play with your happy birthday, David. I will have occasion actually in the evening to express my thoughts and feelings about what you have done for us in India, for Indian science. So for the present, I just would like to say happy birthday. So I want to basically tell you something about the problem of computing S matrices in Chern-Simons theories, which is not an obvious. I mean, if you start calculating S matrices using the standard rules of quantum field theory, you will land into a lot of difficulties with things like unitarity and crossing symmetry. So how to rescue unitarity and crossing symmetry is the main purpose of this talk, and this work was done with Shiraz Minwala and other collaborators, postdocs and students a little while ago. Okay, so the two theories which I would like to sort of focus on in this talk are basically, do I have a pointer here? Never mind. Thank you. Basically, Chern-Simons theory, level K coupled to bosonic matter, and all this matter essentially is in the fundamental representation of let's say SUN gauge group, and these parameters over here B4 and MB square can be tuned to take this theory to, for example, the interesting Wilson-Fisher fixed point, which is the one I will be discussing. And then there is this standard fermionic theory coupled to Chern-Simons with a regular mass term over here. Now there are various reasons to study Chern-Simons theories, especially in the large n limit. Of course, it will be fantastic if we can solve these theories for finite n and k, but even in the large n limit, the problem is not very easy to solve. And I will basically in the first few slides tell you the some of the results actually of the efforts that have been made in the past few years. So we have many reasons for doing it. Firstly, solving a large n field theory in 2+1 dimensions is very desirable. Then this theory also has duality with higher spin theories in the bulk, Vasiliev type of theories. And there are applications to condensed matter physics, and they can be actually, these are vector-like theories, but they can be a warm-up to understanding the ABJ theories, whose solution would be really an extremely important problem to solve in string theory. Now, in all these attempts, a very important result has emerged, and that is Fermi Bose duality in 2+1 dimensions. Now, Fermi Bose duality in 1+1 dimensions is very well understood. It has a long history, and there it is a particle soliton type of duality. Here the duality is between fundamental particles that actually occur in the Lagrangians of fermions coupled to both to Chern-Simons and to bosons coupled to Chern-Simons gauge fields. And the duality basically is the following, that the various quantities like correlation functions, partition functions, etc., map into each other in these theories. These are complicated theories, provided we make the following transformation, that the level goes to minus itself, and the rank of the gauge group is shifted thus, it goes to mod k minus capital A. Sorry? But if I look at large K, that shift is not relevant. Okay. No, it's on the nose. I mean, I'll explain that actually. Exactly what this matching is, I will explain. I mean, just so there are three things I will basically briefly summarize before I give the talk on this S matrix. There's a spectra match actually in these theories. Then there's a duality of the 3-point function of gauge invariant higher spin currents, and then there's a duality of partition functions. So the first point is that if you compute the spectrum of these two theories, both interacting theories, then the spectrum turns out to be just this, basically. Okay. This is the dimension, this is the spin, and the spectrum is independent of lambda. And I think this is the first indication one had that there is some mapping going on between these type of theories. Besides the fact that the bulk theory also gives some indication of Fermi Bose type of duality. But this is a very striking and very nice result actually, which is true at large n. Then the second result, which plays an important role in this subject, is the fact that if you take the 3-point function of higher spin currents in the fermionic theory with this gauge group and level, then this correlation function is identical to this one, and this was proved by these authors using the fact that these higher spin currents are actually partially conserved in the large K limit. So there is a partial conservation which was established in the previous works, and that was used to prove this equation. And so the 3-point function actually being satisfying this type of property is actually a very strong evidence that the full theory might have this duality. And the third one was, so if you compute the partition function of this thermal partition function of this theory on S2 cross S1, then this is the result, that the partition function exactly maps onto each other, provided we make these transformations over here. Okay. And in the above, at least in the simplest case, the bosons are at the conformally invariant fixed point, and the massless fermions are actually coupled to the respective Chern-Simons gauge field. So this in the simplest case is true, but this is true in much more generality, as was later shown by Minwala and collaborators. Even when you deform the conformal field theories, this type of duality happens, provided the other parameters also map into each other in an appropriate way. Okay. Now, yes, I think so. I agree with you. That's what I said actually, that you can even mass deform or these or even deform by a chemical potential these Lagrangians, and appropriate duality transformations can be discovered for the partition functions to sort of match. So it looks like from the conformally invariant point you can move out into some small space in which this does work. Yes.
Just large n statement, or you know if
The proof is in large n.
you don't know?
No, I don't know. But yeah, I don't know. But the proof is in large n only. Okay. So I just want to make a couple of statements about pure Chern-Simons theory, which before I move on. We all know that this theory is a topological field theory on a tree manifold, and it exhibits a very remarkable duality. This is called the level rank duality. You take a Wilson loop in the UN theory at level K in a representation R, and that average actually in the Chern-Simons action is the same as the expectation value, provided you provided the gauge group rank is mod K minus n, level is minus K, and the representation is R twiddle, in which R twiddle is obtained from R simply by interchanging the rows and columns of the Young tableau that represents the representation. And this, it is in fact this duality, which is true in pure Chern-Simons theory, gets lifted in some way, in an important way, in the stated Fermi Bose duality of the partition functions, which I actually mentioned before. So this is an important fact about Chern-Simons theories. The other important fact about Chern-Simons theories, which will be relevant for us and we'll use it, is the fact that if you compute the square of the Wilson loop, as for a simple Wilson loop, simple means topologically the same as, let's say, S1, W square expectation value, it is the same as the square of the expectation value, and it evaluates exactly to sine pi lambda upon pi lambda. So I'd like you to just keep this in mind, that the ratio of W square to W expectation values is identical to sine pi lambda upon pi lambda. And this is the exact result actually for any finite n and k, but also valid for large n and large k. Okay, with these preliminaries, I'd like to, before I tell you some results in detail, I want to summarize the result of these works. So we are interested in the scattering problem of fundamental particles in this theory, means fundamental boson, colored objects scattering, colored fermions and colored bosons. So we are interested in 2s matrices to begin with, and we would like to calculate them. And we all know how to formulate the problem of the calculation of the S matrix. So we would like to show that for large n, for all allowed values of the 't Hooft coupling, these are the results. So the S matrix can be calculated in ST and U channels as usual. So so one can actually, in the large n limit, compute the S matrix in the T and U channel. That can be done. These answers are unitary and they exhibit Fermi Bose duality, okay, which I will detail a little bit later. So this is the first result. Now the surprise is that the S channel S matrix cannot be obtained from these answers by crossing symmetry. Usually we go from S to T to S channel using analytic properties of the correlation functions. In this problem, what happens is that the S matrix is not analytic. And it turns out that it's not analytic because unitarity requires a delta function in the forward scattering. And this is a very old problem, and I will detail a little bit to you about this is the Aharonov-Bohm effect basically. And the reason it is the Aharonov-Bohm effect is because the Chern-Simons matter theory has a very fundamental equation which says that the charge density, the colored charge density, is equal to k upon 2 pi times the field strength, which basically means that every charged particle carries magnetic flux. So we are basically in the spectrum ions. So when you talk of scattering of these type of particles, you have to worry about the Aharonov-Bohm phase. And it so turns out, as I will mention later a little bit more detail, that the Aharonov-Bohm original paper of 1959, the S matrix there is not unitary. And it took about, this gentleman, Rüscheners, many years later, pointed this out and actually added the right piece in the Aharonov-Bohm answer to unitarize it actually. So this is something which one had to sort of discover through the literature. Okay, so this delta function being there tells you that there is no analyticity, and therefore you cannot really obtain from these answers the S channel S matrix. Okay, let me go on. So the next point I'd like to make is that the standard LSZ formalism for quantum field theory fails here because of Gauss's law again. because the Chern-Simons gauge field never really gets decoupled. You see, you apply lazy formalism if you can switch off the interaction, and you have particles in a free Hilbert space sort of scattering, there is interaction, and that's how you define the S matrix. But here, since you cannot disentangle the gauge field from the matter particles which you want to scatter, you cannot use the standard LHC formalism. And so we have a certain proposal of what the S matrix definition should be, which I will come to later, which is basically dictated by gauge invariance. Okay. Now, so we have a proposal for an S matrix in the S channel which we cannot calculate because for reasons I will mention. And this proposal, of course, passes many very non-trivial tests. It passes the very nonlinear test of unitarity. It has Fermi Bose duality, and also it has a correct non-relativistic limit. But as I said, as of now, we do not know how to really compute this from first principles for reasons I will mention. Okay, so here is the answer for the S matrix in the S channel. So you take the T channel S matrix and apply the standard rule. This is what I call T trial, and then you fix it by this factor, which is the expectation value of the Wilson loop in the Chern-Simons theory, and this factor over here, which is the delta function in the forward scattering with a very specific phase over here. This -1 is because basically what is happening is that I am writing the S matrix as 1 plus IT, but actually what is happening here is that the S matrix is not 1 plus IT. It also has the fact that there is forward scattering because of the presence of the anion. Okay, so this is the formula, and this is some result of a calculation, and it is this S matrix that satisfies all those requirements which I actually mentioned before to you. Yes. So that there's another thing is not only the delta function but also this normalization factor, which I will explain how it comes actually. Okay. All right. So now let me just describe to you the basic preliminaries of how to set up this scattering problem. So we consider the scattering of massive colored particles. Particles transform in the fundamental representation, antiparticles in the anti-fundamental representation. There are three distinct scattering processes actually: particle going to particle, antiparticle going to particle, antiparticle, and anti going to anti. And all of this can be extracted if one knows the 4-point correlation function in different regimes. So the main object of computation really is this 4-point function, and I'll just try to set up the kinematics for you just to explain that at the exchange of one gluon, this is how it looks basically, and this is the particle-antiparticle process, and there are two channels here. One is the adjoint channel, which is like this, and then there is a singlet channel, which is in this way. Sorry. The important point over here is that in the singlet channel, this momentum q. So if you compute higher and higher orders in the ladder diagram sum, you will find that this guy, this q, simply hangs on. So in some sense, it is a conserved momentum of this set of diagrams. Now what happens is that if you set it to 0, the calculation simplifies enormously, but you cannot do that in the S channel because it is simply the center of mass momentum. You cannot set the center of mass momentum. I'm sorry, excuse me, I made a mistake actually. So I'll just you don't set it to 0, but what you do is basically over here. So the integral equation which which I do not want to discuss further, because you can just set it up. It's just Schwinger-Dyson equations. But these integral equation for the T channel and a U channel can be solved, provided you use the axial gauge, the light cone gauge, and you set Q minus equal to 0. Okay. But you cannot do that actually if Q is the center of mass momentum, and this is the main reason why this integral equation is difficult to solve, not impossible perhaps, for the S channel. So this is the reason why the S channel is not calculable from first principles, but the T and the U channels are calculable because of this kinematic trick. Okay. All right. So as I said, you can go to a Lorentz frame with external momenta Q plus minus equal to 0, and compute the T channel, which has the adjoint representation passing in between. But you cannot do that actually for the other fellow. And then you can reconstruct the entire S matrix from Lorentz covariance, and you find that for the T and U channels, they satisfy unitarity and also this duality, provided the fermion mass and the boson mass are related this way. This critical is here because for this talk I am basically working at the Wilson-Fisher point for the bosonic theory. Okay. Now let's discuss the singlet channel, which is the main object of our discussion. So I mentioned before already that the kinematic simplification cannot be done for this, therefore you cannot solve this from first principles. And as I mentioned already in the summary, that yes. Yeah, that's exactly. No, you have to. No. The point is, I think that you need. We know the S matrix actually, on shell S matrix in the T channel. We do not know the on shell. You do not know the on shell S matrix in the S channel, because you cannot continue it. So there is a formula we provide for the S channel in which the trial S matrix obtained from the T channel is multiplied by this normalization factor, and plus you have this delta function piece. Yes. 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 Everything is leading order over here. Yeah. Okay. So let me go ahead. All right. So so let us just go a little bit and look at the non-relativistic limit. So I just want to discuss very briefly the Aronoff-Bohm problem actually, which is the scattering of a unit U1 charge of a magnetic vortex. Okay, and as I mentioned to you before, the addition of the delta function in the forward scattering was noticed for reasons of unitarity by this person in '83, and in the non-abelian case it was discussed by Bach, Shakib and So-Young-P. And what they found, and this is an important formula for us, that if you take the non-relativistic scattering of two anyons, basically the scattering amplitude is the same as in the case of U1 charge scattered off a vortex with this flux. These are the Casimirs of the representation. So if you take R1, R2 representations and you break it up into a sum of, you decompose into other irreducible representations, then this is the sort of formula for the effective magnetic flux that you need to get the right answer. And this is very simple to understand. And now if you look at the non-relativistic scattering amplitude, it is basically given by this formula. So this is the additional delta function I was talking about, and here is the rest is the Aharonov-Bohm answer. And if you compute now the effective magnetic flux in the adjoint and the symmetric and antisymmetric channels, it is basically 0 for large K. It only survives for the singlet channel, and this is why we need the delta function for unitarity in the singlet channel. But at finite n and finite k, I think this this type of answer obviously survives for the Aharonov-Bohm in the non-relativistic case, even for finite n and finite k. But since we are working in the relativistic theory at large n, this is the only case of interest to us. Okay. Now, there is a very simple reason why this delta function is there, physical reason, and why its coefficient is given by cos pi lambda minus 1. So just imagine that you have this vortex over here of some magnetic charge nu. Then the particle scattering, you know very well that if you go around it, you will pick up a phase. So for particles scattering slightly above and slightly below this vortex, which you need to regularize in order to make this argument, the phase is basically e to the I pi lambda and e to the minus I pi lambda. So these two phases basically add and you divide by 2. This is the intuitive reason why you get a cos pi lambda over here. Okay, so and this phase is independent of the speed of light. So it would, if it is there in the non-relativistic theory, it has to be also there. It's very likely to be there in the relativistic theory also. Okay, so this. No, so exactly, right, exactly. That's what I said in the beginning. That usually you have S equal to 1 plus IT. Now it's not 1. I see. Okay. All right. Now, how much time do I have? Oh, I think I will run through all this very quickly. Basically, so you can actually check that the answer I have given you is, the Aharonov-Bohm answer turns out to be unitary by just some basic algebra. And now let me explain this. This is the other thing which I would like you to take home with you. How do you get that normalization factor? So, we do not have a solid calculation for it, but here is a good physical understanding of how that normalization factor of sin pi lambda upon pi lambda comes about. So since we are discussing the S matrix of colored particles and the gauge field cannot be switched off asymptotically, we need to define a certain process in order to extract this S matrix from a manifestly gauge invariant procedure. So we do the following actually. Okay, just imagine, let's go Euclidean in the sense that let's work in Euclidean space-time for the moment, for the sake of this argument, and look at a large S2 sphere in S3. Okay, and think about these points x1, x2, x3, x4 are the points from which the scattering particles actually emanate into the bulk of S2. Okay, so you'll have particles going from here to here, they go around, wander around, intertwine. So this is the T channel basically. Okay, so you take these particle lines and gauge invariantize them by adding a Wilson line over here, and the same you do over here. So this is the T channel. For the S channel, what you do is the same thing, but in the S channel, the particles go from x1 to x3 and x2 to x4. Now, clearly, I mean, this is just a symbolic way of saying that there will be clearly, I mean, the particles are just not going from x1 to x2. There's a lot of dynamics happening. There are lots of intertwinings going on inside, but in the large end limit, there is a very interesting simplification which comes from the Skene rules of Jones in knot theory, that if you want to, if particles want to cross each other, then they just pick up a phase. Okay, and in the large end limit, this is an exact result basically. Okay, if n and k are finite, one is unable to do this, so one is unable to proceed further in this problem. So now that you have this type of a rule, basically all these particles, all these paths can be shifted to this set or that set with phases. Those are the Aharonov-Bohm phases. But you see, the topology of paths is very different in the T channel and the S channel. Okay, and so therefore our proposal is that is precisely the ratio of the S matrix in the S and T channel is given by this, you know, because in one case you have 2 Wilson loops, in the other case you have 1 Wilson loop, and so the S matrices come in this ratio, and this ratio is precisely calculated for Chern-Simons theory long time ago by Witten, and it's exactly this. So in this way we justify the appearance of the of this factor, this sin pi lambda by pi lambda in the S channel S matrix, and if you do all this, then you satisfy unitarity, you satisfy duality. So we have a good answer without a first principles derivation actually. Yes. Large n. Only large n, because the Skene relation has 3 terms which are very complicated. So the third term just drops out at large n. So the particle just passes through with a phase. So this is why we can make this argument. Oh yes, okay. So at finite n, I don't think I can make this argument at all actually. In fact, yes. Yes. Right. Right. So I think the answer to this is that if you do this, then the S matrix satisfies unitarity and duality. I mean, this is just in some sort of a physical reasoning why the ratio is just of the square of the Wilson loop by the Wilson loop. It's just that actually. So it's not a proof. It's just suggestive, but you arrive at this answer, and then you can sort of satisfy the very nonlinear relation of unitarity. Both of them you need for that actually. Question, sorry? Why not? Yes, exactly. So, no, I even at yeah, I agree with you. I think we are not scattering neither bosons nor fermions. We are scattering just anions, basically. So it never goes away. Okay. All right. Okay. So The rest of the talk is basically showing you lots of formulas for these matrices, which I will just skip very fast. I mean, the essential point has been made. Then you do it for bosons, you do it for fermions, and what I have said, that the T and U channels, everything works out analytically, means you can do it. For the S channel, we have these working rules. We find that the S matrix is unitary and satisfies duality. And then I just wanted to mention that Shiraz and collaborators have also studied the S matrix in supersymmetric fields. Okay, so I mean, the supersymmetric theory, you can think of the S matrix as a superfield, and let's say for n equal to 1 theory, and this very beautiful result that the supersymmetric Ward identities determine, all these, there are 8 S matrices basically for various combinations of particles, and all of them are determined in terms of the basic bosonic and the fermionic S matrix, and this is a lovely result, I thought. And for the n equal to 2 theory, it is just entirely just one function, because there is a relationship between even these two, and there are some very interesting things over here which I don't want to just let me tempt you, that the S matrix in this theory actually has massless poles. There are new massless particles which one doesn't know, which one has not been able to understand, at least the authors. We have been discussing this, but yeah, so this these calculations can all be done for supersymmetric theories also. And this is important because ABJ theory, you want to really include all the supersymmetric particles also. Okay, so my conclusions are basically that the critical bosons and fermions and deformations can be calculated, and they are all consistent with unitarity and with fermion boson duality. And okay, so all this I have said. Now, what are the implications for ABJ theories? So, Shiraz and I were discussing about the non-relativistic limit. Any relativistic theory has non-relativistic limit. You do that, you find that you need the delta function in certain channels. Okay. Now, I also think that studying odd number of Majorana fermions coupled to Chern-Simons theory is an important problem for condensed matter physics, and thinking about it, it's not easy how to do it. But anyway, so it's an exciting area, and thank you for your patience. Thank you. Yes.
Any idea what that
is? So when you do ABJ theory, you have these other representations, right? No, I mean, see, so yeah, that's true. So I think people have been working in perturbation theory for the joint representation, for example. But as I said, if you take the non-relativistic limit, you can have a definite conclusion even about ABJ theories, because it's just the Aharonov-Bohm problem for other representations.
I looked up that many years ago.
I see.
Then you find that basically the linking number of representations, you can express it.
Yes, that's, yeah, of course. You have any comment, Shiraz? I mean, especially for the n equal to 2 theory. Yes, you see, I mean, certainly you can make, for example, this theory has gauge invariant currents of higher spin. They create their own states. You can scatter them. That is the sort of scattering you are talking about. No, I agree with you. But we are deliberately trying to understand the scattering of colored objects as a way to, understand the duality map via the S matrix actually. That's what we are trying to do. So, yeah, is that clear? That's an object to compute, I mean, yeah. Yeah, I would think so. Yeah, I would think so. I don't know. Should I ask? Shiroman, some results, but not exactly. Yeah, yeah. Right, okay. At certain points.